Yeah, the base.
All right, so I guess this is going to be sort of an introductory talk. I don't even know if I'd call it a talk, but I guess I wanted to sort of show how you can use Haskell's type signature to have more control, or to restrict what functions are allowed to do. And based on how polymorphic a function is, that sort of will constrain what the function is allowed to do. And so we're going to sort of play a little bit of a game where I'm going to give some type signatures, and I'm going to ask you guys, like, what does this function do, or what is this function allowed to do? Okay, so I'm going to start with a very non-polymorphic function, so a function that uses very concrete types. And okay, so here's a question. What does this function do? Okay. All right, so it's sort of a rhetorical question here, but I mean, if we're implementing Wrangle, we're given this concrete type int, and so we know we're dealing specifically with an int. So any function that is defined on int, we could potentially call in the body of this function. And we're also free to just completely ignore the input parameter, and just always return 42, say. So we do. So that said, we do know maybe a few things. So we know that this function, it can't launch the missiles, or it can't write to the file system, because if it were going to do those things, we would have to return IO. So we at least know that it's a pure function. But other than that, we can't really say much about what this function can do. Okay, so I guess the way I think of when you're writing a function that works with concrete types, like int, the implementation of the function, you're given this entire universe of functions that you can call for that concrete type. And the type checker, Haskell's type checker, won't prevent you from calling any of them. So I could call, I could say 1 plus x here, I can return 42, I can do whatever. Okay, so let's look at a more restricted type here. So if I give the type foo, and this is like implicit, that if there's a lowercase type variable in the type, and I don't, and I don't say what it's bound to, it's implicitly quantified over. So I'm saying for all a, given an a, I need to return an a. So anyway, what is this function?
It has to be the identity.
Okay. So so it has to be the identity function. I can say foo equals ID here. Okay, so the way I sort of like to think about when you're writing a polymorphic function like this is that instead of starting with this whole universe of functions that you can call on int, which is this huge number of functions, when you're polymorphic in one of your type variables, you actually start out with not being able to call any functions or construct any values of that type. So instead of starting with this huge universe, you're sort of carving out this tiny little universe of possibilities. And the type checker will sort of, sort of like Bumpers and Bullet Notes, sort of the title of this talk. The type checker will prevent you from assuming anything beyond the possibilities that you set up for yourself in the function. Okay, so that's kind of I feel like that's a very nice default to start with nothing and sort of only add what you need, rather than when you're working with concrete types, you're sort of starting with this, huge set of things, and hopefully you only use the ones that you actually want to or need. Okay, so let's look at another example. So I'm sort of deliberately using meaningless names for these functions because I actually want you to not use the names to reason about what functions might do and just look at the types. So what about this function? What is its implementation? Okay, and can someone explain like why that is the only implementation? Yes.
Because all you have is one A, and you need to give two A's, and you can't call anything on A or make a new A or grab an A from anywhere else. So you have two slots to fill in, one thing to fill in one.
Yes.
And Tom only has one constructor.
Yes, that's true. Yeah, so you can't just, conjure up an A at a full clap. You're only given one A in your sort of local environment, so you have nothing that you can do other than just put that same value in both places. Oh, yes, that's true. I could say int A here.
You can also all plus A.
You could spin forever, but
This is still the same function, just
Yeah.
multiple algorithms.
Or error out.
Yeah. Okay, yeah, so you could also do lots of evil things like, call unsafe, perform IO, and do things like that. So you could actually launch the missiles in Quarks, but we're gonna ignore that. We're only gonna start talking about well-behaved Haskell programs. Okay. All right, so what about this function? So how many possible implementations does this have?
There should be two.
Okay, and what are they?
It either equals A1 or it equals A2, because you have two different values of type A.
Mhm.
You can combine them anyway. You don't have a function available to do that. So you need to return one or the other.
So one thing that's kind of interesting about, so you can sort of look at this type signature and just think about what is the information that is contained by an inhabitant of that type. So in this case, this function, it only gets to make one decision. It's sort of one bit of information. It can either choose the first thing or the second thing. So this type, for all A to A, is sort of, it contains the same information as just a Boolean, say. Does that make sense? Okay, so that's sort of interesting. I'll talk a little bit more about that later. Okay, let's look at another example. Okay, let's call this W. So notice if I say, if I write this signature, W, A to B to B, then this is back to only having one implementation, right? So it has to return the second argument. And so one of the things you notice when you're working with polymorphic functions is that a lot of times it's actually better to generalize your functions even before you necessarily think you quote unquote need it. So I'll sort of give an example of this. So I might have some sort of point class, maybe I sort of happen to know or think that I'm only going to be interested in points containing two doubles. And so, I write something like this, point double double. So it's just sort of specialized to double. But now notice the type of getting the x coordinate of a point is now sort of less informative. Now it's just point to double. And now it actually has two implementations. So I could actually implement it like this incorrectly, right?
That's one implementations.
Yeah, right, so, that's true, yeah, so lots of implementations. So very often, it makes more sense to, even if you know or think that most of the time you're going to be sort of interested in some particular instantiation of a polymorphic type, a lot of times it pays off to just be more polymorphic in the first place, because there are going to be some functions like X that
I think your type signature.
oh, sorry, yes, okay. So there are going to be some functions like X that don't really care about the type of the point. And by making these more polymorphic, you can actually give more precise types and get more help from the type checker in in implementing your various functions. Like it's a very common thing. Yeah, you might be writing some more complicated function that deals with points, and by sort of having that function take point x, y, where x and y are sort of parametric, it prevents you from internally confusing x and y dimensions within the body of that function, which is a very helpful thing, and it's just rules out this whole class of implementation bugs. So one thing you often, or I think this has been pretty much discredited at this point, but like Joel Spolsky was sort of big on Hungarian notation, where you label, you prefix any sort of x dimension with x and any y dimension with y, and then if you're, if you're working with the code, you can sort of see by visually inspecting that, oh, you're passing an x thing to something that's taking a y thing. That looks wrong. But that's just sort of a bad approximation for, just using the type checker to actually check that thing for you. So it's not something that a human has to visually inspect. It's something that is actually going to be verified on a compiler. Okay. So, any questions so far? No. Is this like, so just like a show of hands, is everything I've said just completely straightforward and unsurprising to people, or is this interesting to people, or? Okay, all right. Okay, so here's a question. What is wrong with this type? Yeah.
Empty list. That's that time.
Yeah. So exactly. So what do I return? When given the empty list, I can't just conjure up an A out of whole cloth. So whatever this function does or purports to do is going to be misbehaved. When it's given the empty list. Now, Haskell has like an evil. Some evil functions that you can use. You can just say error, an empty list here, and then you'll get an exception. But that's sort of like subverting, Haskell's type system. It's sort of evil. Okay. So, that reasoning was just entirely based on just looking at the signature. I can just look at the signature, and I know that phunction is sort of misbehaved. Okay, so this function actually, we actually have something that we can return in the event of the empty list. And in fact, that is the only thing that we can return in the event of the empty list. I mean, we don't know what this does for this case, but that's fine. Okay. Okay. So earlier I mentioned that this type for all A to A sort of contains the same information as bool. So let's look at another example. So if I have for all A to maybe A, what is that, what information is contained by that type? What, so somebody says it's N, right? N?
A positive integer or zero.
No. It's any function from an integer to an integer less than or equal to that, or less than that number, right? Because it could pick any, given the length, it could choose a different number. You might have a list of 6 elements, and it might choose to take the 4th one on a 20-element list. It might take the 15th.
But that is, the function, it's deterministic, so it's always going to return the nth element, whatever n is. So if I define...
No, because I can count how many elements you've given me, and then I can choose a completely different element based just on the length. I have a function from int to a number
True. No.
smaller than the int that, or up to the int that I was given.
Okay, no, yeah.
That's the, did I spoil a punchline?
No, actually, I actually didn't even think about that, but that is, yeah, so it's, I guess it's sort of, I guess it's kind of, it's, well, it's like NAT.
You have to give me a NAT, and it's not to an arbitrary NAT, it's to,
It's like
you
a
need
NAT less than or
you need to
equal
put the little
an
pi
integer.
type on it, right, yeah.
Yeah, so it's like, you give me a natural number, and I'll give you
In
a natural number which is less than or equal to that natural number.
Mhm.
Okay, so, yeah, I guess I find that to be just an interesting perspective of sort of think of like, what is the information that is, or, you know, what is the information that is encoded by a value of that type? So, and you just think about what are the decisions that it is allowed to make?
In this case, it's less than or equal to, actually, because you have the nothing case. So you
Yeah.
should-
That's like we can't really write this,
It's,
but
oh, yeah, NAT less than or equal to X, yeah. So the
It's
next
something like that.
Then it's like,
Okay, so here's another question. So what is the implementation of this function?
Empty less is always...
Yeah, so we can't fashion bees out of whole cloth, so the only thing that we can do is, return the empty list. And so this sort of reasoning that we're doing is, it's sort of it rests on the fact that when we're quantified over some type variable, A or B, we really don't have any operations or values available to us that aren't explicitly passed in. So as soon as you have a language that has some value like null that inhabits all types, or has operations like equals and hash code that are also for some reason defined for all types, the reasoning that we're doing kind of goes out the window, and you can't really do that same reasoning. So if this were Java and we were and we wrote a function with this signature, we could actually compute the hash code of each element, remove duplicates, and then based on the number of duplicates, return that number of nulls in the output, say. Now, I'm not saying that's a reasonable thing to do, but you could. But technically you could, okay.
I suppose in Haskell you could just have a list of undefineds equal in length to A.
Yes, but
Well,
let's
that's-
pretend that undefined is
You have fast and loose reasoning is morally correct. You can always appeal to at the end of the talk. To
Yes.
point out.
Yeah, there is actually a paper called Fast and Loose Reasoning is Morally Correct, which sort of formalizes what I'm kind of alluding to, which is that we can pretend that infinite loops and exceptions and so forth sort of don't exist for purposes of reasoning about these type of methods. Yeah.
Did you say the title of that paper? Oh, yeah.
Oh, it's called Fast and Loose Reasoning is Morally Correct, I think. And I'll try to send around some notes after this with these things. Okay. All right, so here's another question. So I'm going to give a function signature that has sort of 3 reasonable implementations. And I want you to tell me what they are. Okay. So we have a list of A, a list of B, a list, we need to return the list of A, B. So 3 implementations, so somebody name one of them. Zip. Okay. So high equals zip. What else?
Zip is partial though.
Well, it just throws away some information.
Yeah, so zip trims the output to whichever input list is shorter, but that's fine.
Cartesian product.
Okay. So what's the implementation? Speeds.
The easy way.
Let's do this one first.
Left A2, comma.
Okay. Yeah. So let's look at let's pick some concrete types here. So 1, 2, 3, and let's say we have a list A, B, C. So what that's saying is, okay, we can form all pairs of the 2 lists. So 1 A, 1 B, and then 1 C, and then 2A, 2B, and so on. Okay, so that's sort of one reasonable implementation, but another reasonable implementation would be, instead of doing 1A, 1B, 1C, we could actually do 1A, 2A, 3A, and then 1B, 2B, 3C, right?
Not all the other possible inputs.
And yeah, I mean, we can do some
You do little
arbitrary.
diagonal
Yeah,
things
yeah.
so that you don't.
But yeah, so I guess
ordering.
that's why I said sort of reasonable implementations, because yeah, some random arbitrary interleaving or way of ordering would be kind of unreasonable. Or I mean, not saying you'd never do it, but I guess when I look at that type signature, those are the possibilities I might think of. Yeah, so Ed mentioned that this would be lift A2, A's, B's, so that would be the 1A, 1B, 1C, right?
Yeah.
And then the other implementation would be, I guess it'd be maps. Oh, or I guess we could
Map
just do,
flip.
yeah, let's do
Map, and then you flip the arguments.
I was gonna do like this or swap.
No, I was just gonna lift A2, flip, comma,
Oh, okay.
and then you flip the whole thing on the outside. No dot, just flip it. And you can A to reduce the A's and B's if you want.
Yeah.
And just flip the whole thing.
Like,
No flip on the, one flip on the inside, one flip on the outside.
on the outside here?
Yeah.
Oh, map flip.
No, you just want to flip the whole thing. High equals flip of, lift A2 of flip, comma.
Get rid of the A's.
You can get rid of the A's and B's.
Oh, I see.
That way flip is being used to swap the argument order. Flip the
Well-
expected result order and flip back. So you have
You
to
could
flip
also
twice.
just do with the A's, B's,
And then you can B's, A's, yeah. You can you can write the outside flip by hand if you want to. But you need one more flip. You need to flip on the outside.
Yes?
Yes. No dot, just flip you want to flip the whole expression.
So
You need
flip
to put your parens on
dollar
everything
sign.
else.
Oh,
Now you're good. Lift.
Okay. Yeah, all right, yeah, okay, yeah, that works.
I've been staring at an awful lot of code that looks exactly like this.
Yeah, don't ever write code that looks like this.
Yeah, I'm unfortunately forced to. I'll explain why.
Okay, so, all right, so let's look at another example here.
How does your fast and loose reasoning deal with things like reverse? Are you implicitly thinking like the list is really a more generic monad and kind of skipping that? Because the list has this thing that's list of A, list of A.
Reverse fits into the fast and loose reasoning is morally correct. The notion of fast and loose reasoning is that if you write a program in a world where everything terminates and everything works and there is no error or undefined, and you write a program that exists in a world where it does exist, right? And both of these programs terminate, then they give the same answer. That's the idea here is that as long as the program that we wrote with ignoring bottoms doesn't give a bottom, then it will give the same answer in a world that does that make sense? So reverse, the only thing that reverse introduces is that there's a bottom when you go to reverse an infinite list.
Well, sure, except that it means that every one of these arguments for
Could be reversed.
list has reversed interspersed any place you go to list A.
You could reverse it, you could shuffle it, you can do whatever you want to it. You can
Yeah.
if you have a list coming in and you're spitting out a list, you're going to spit out some arrangement of the elements from the original list in that final result list, but you have no guarantee about the relative order of them. You just know that every element that you get out is going to be one of the ones you got in.
Okay, so at that
Or less.
point.
Huh? Or yeah, it may be several repetitions, they may be dropped on the floor.
Wait for it to valid chapter THC.
Write it.
So I guess, I mean, general point is that, you know, this type of reasoning doesn't mean you always exactly nail down, you know, what the implementation will be. It's just sort of placing some restrictions or constraints on what you're allowed to do. So yeah, if you take a list, then you're free to reverse it and, you know, do all sorts of things, even if you're parametric in the elements of the list.
So you've got this logical sort of statement that for all these list arguments, it's now true modulo order and repetition. How do I do that in the abstract? Take something like list and get something like modulo order and repetition.
Have you heard of free theorems?
Yeah.
All right, so let's.
But that's
let's,
going to go pretty far afield.
Okay. All right, so let's.
You want a lowercase a, do?
Oh, so I was going to give an example here. So this function, a to b, given an a, returns a b. So this function only has sort of one implementation, right? You know, or just a is equal to $. So all we can do is just apply the function to the argument. If we write a function that takes a concrete a and returns a b, and then we have to return a b, this sort of implicitly, you know, it either closes over or has access to a concrete a, and it can potentially call any function available on a in order to modify it before it eventually calls its input. So, I mean, if we imagine this is in, you know, we can do whatever operations we want on integers before we go ahead and call a function. So, yeah, so a lot of times just being more polymorphic sort of constrains your universe and prevents you from doing sort of arbitrary things in the implementation of your function. Okay, so I wanted to take a little break and talk about, I'm not sure how far I need to get here.
So goo is equivalent to an int.
Yeah. So yeah, I wanted to talk about so-called free theorems, okay? So I'm going to sort of work up to this with a couple examples. Okay, so if I say, so is everyone familiar with the function map on lists? So I'll do a quick demo. So if I say, I'm just going to say fmap for reasons that will be clear later. So if I say fmap 1 plus over this list, it's going to add 1 to each element of the list. And the output type of fmap, it doesn't need to be the same as the list elements don't need to be the same. So I could actually, convert everything to a string in the output. Okay, so my question is, if I reverse the list and then map a function over it, is that the same as mapping the function over the reversed list?
Is the list infinite?
Let's assume a finite list.
Oh, we'll divert you left.
So, sorry. So is it the same?
Yes.
I think so.
Okay. Now suppose I have a function. It's not reverse, it's just wrangle. And it's of this type. Okay? So now if I say wrangle map f x's, is that going to be the same as map f wrangle x's?
Yes.
Okay. So why is that true?
This is the opening example of Otto's favorite.
So can somebody give some intuition for why
Yeah,
that's
well,
true?
because Wrangle doesn't know what's in the list, so whatever Wrangle does to the list, it's going to either affect the order or duplicate elements. I mean, as we discussed before, there's only certain things it can do. Those behaviors are completely agnostic to what's in there. Because map doesn't change the order, I mean, whatever, let's just say it permutes the list, and the permutation will be the same whether we do it before the map or after. Because map is order respecting, so.
Right.
It's-
Yeah, exactly. So whatever Wrangle's doing, it doesn't care what the elements are that are in the list. So, whether we transform them before or after, it doesn't really matter. So that's kind of an interesting theorem that holds, and I just sort of read that theorem off from the type of Wrangle. So, the type of Wrangle is just for all A, list of A, list of A. And from that, I get this free theorem that that I can sort of apply Wrangle before or after mapping. Okay. So this can be any f, or not f. Let's pick B. R. So that can be any R in here. And usually, the way you'll see this sort of thing written is instead of mentioning x's, you'll just say,
You have an F there or you want.
Yeah.
oh, sorry. Yeah, we'll sort of write it point free. So we'll say r dot map f is equal to map f dot r. Oops, r. So it doesn't really matter what we call that. List variable. Okay, so let's look at another example. So let's suppose I write safe head is A and maybe A. I say safe head of empty is nothing, and safe head of that is just H. Okay. So now let's ask a similar question. Changing these to F maps. are these two things the same? So,
No.
Should be.
so just to demonstrate, so if I have f map of 1 plus over nothing, that's
Okay,
nothing.
then it's fine.
If I f map over just 4, we get just 5. So f map lets us sort of map within the structure of whatever type we're talking about. Okay, so this is
So
saying.
wait a minute.
Yeah.
They're not the same because F, what is, if X's is a list, then F in the first instance is taking the actual, I think you have a type problem there.
They're different F maps.
Okay.
So yeah, so
But they're both trying to map F.
yeah, so let's
Yes.
let's kind of deconstruct it a little bit. So
Okay.
Are we assuming that our functor instance for X's obeys the functor laws?
yes,
This is usually given in terms of the natural map, which is what functor should be.
so yeah, on the left side, what we're saying is, so X's is a list. So we're saying, okay, map over the entire list some function, and then take the first element safely. On the right side, we're saying, take the first element safely, and then map over the maybe. So now you're mapping over a different thing. You're mapping over a maybe versus a list, but we're still sort of doing mapping. And so once again, I'm going to ask the same question: is if I have A to maybe, so is it the case that foo.fmap is equal to fmap.foo? Yes. Okay.
Yes.
And yeah, it's true it's by the same reasoning that whatever foo is doing, whether it's taking the head safely or taking the 14th element safely, or doing whatever, it doesn't really care what the type of the elements of the list are. Okay, so that's an example of a free theorem that we can read from this type, just from the type. We don't care about the implementation. And sort of more generally, so here's a very general way of stating free theorems. So if I have a function R, which goes from some f of a to some g of a, where f and a and g of a can be anything, actually, anything that's a functor, then it is the case that r.fmap f is equal to fmap f dot r.
Can you call that a natural transformation really quickly so I can use that in my next talk?
Yes, and R. So one second. So this is kind of the most general statement, or I don't know if this is the most general statement of how you phrase free theorems, but all sort of free theorems have this sort of form, where you pick some f and some g, and you have a great deal of flexibility in what you pick for f and g. So here, for foo, we picked f was list and g was maybe. For reverse, we picked f was list and g was list. But we could also do things like you can pick say the constant, this data type, const. ignores its second type argument. And with a data type like this, you can prove things like, it becomes a free theorem that you can compute the length of a list either before or after mapping and get the same result. So if we were, so the connection to category theory is that any function which is, any sort of polymorphic function, which you can sort of phrase in this form, R is of type, converts from f of a to g of a. You can view it as a natural transformation between two functors, and this has deep connections in category theory, and I'm not going to talk about that here, but yeah, I mean, this is a nice way of sort of seeing that, that you can, seeing the sort of free theorems that you can get just from reasoning about the types. And I think that's pretty much all I was going to say. So any questions? Yes.
In practice, we programmers are often told once, twice, thrice, refactor. Write the simplest thing, maybe the most specific thing, and then discover the generality later on. But what you're proposing is the exact opposite of that conventional wisdom, and I wonder how you found that in your daily programming to try to be the most polymorphic first.
Yeah. So, yeah, I think that rule is sort of a little too simplistic. I mean, so yeah, I think as I've sort of said, it's like there are advantages to being sort of more generic than you maybe think you need. I mean, I don't necessarily endorse like coming up with just some half-baked abstraction that you haven't really thought about, but at least when you're writing functions, I mean, if you can make them parametric easily, then I think it's a good idea to do so. And especially in functional programming where, Haskell, you can pass functions around very easily, and it's just very easy to write code that's polymorphic. There's really no reason not to do it. I think a lot of that rule of thumb, I think to some extent it comes from sort of old school OO,
Yep.
Where like
Yep.
languages without first-class functions and, without good type systems for these things, and it really is a pain in those languages to abstract code. But yeah, I mean, in Haskell and in FP, if you're using a decent language, then it's pretty easy. So yeah.
Is there any entire class of free theorems, or you mentioned this is all free theorem? Are there others?
So
Yes.
yes,
There's a grown-up version of that.
yeah, but this form, I mean, this captures a lot. So I don't actually know.
That captures the form of all natural transformations, basically. In theory, you can have your free theorem depend on other free theorems. Basically, you give me that f dot g equals something commuted over, like this other pair of things, and then this free theorem follows. And stuff. And that happens when you actually make use of more variables and whatnot.
Okay.
So when you just have the one type variable, they all kind of look like this. When you have more, then they get uglier.
Right.
And if you use the free command on LambdaBot or whatever, it's doing that.
One thing I was going to say is a lot of times when people, so there have been a number of cases that people write papers and they say, I have this type class and, or this interface and it needs to satisfy these properties. And, it'll be discovered later on that, actually some of those properties are just free theorems that are just guaranteed by just the types that are given. So I guess the point is that a lot of times these theorems are somewhat surprising. I mean, the consequences of parametricity are sometimes surprising. Yeah.
One question, back in your early example, your point with the constructor that has the two generic types,
Yeah.
I mean,
We deleted
was
it.
there really a big advantage to having both the A and B type variable? Normally they'd be the same type.
Oh, so I mean, that was kind of what I was saying before, is by making them separate type variables, you can write code that you're sure doesn't accidentally mix the two.
Okay.
If you get it down to one type variable, you've at least you've limited yourself to one thing you can do, right? You only have one way to cross the streams.
Yeah, also kind of related to this is, so something like, this function, which actually exists. That's what it's called on data.set. So this signature is, you know, a lot of times you'll see these signatures like this, where like, you know, it'll take like 3 ints, and you're like, well, the hell do all those ints mean? And like, maybe you can like go read the documentation and figure out that, oh, this first one means this, and the second one means that. But you know, the type checker is not going to help you out or force you to make sort of an explicit decision about what each one means. So a lot of times what you can do in situations like that is, so maybe I'll give another example, like, so double to double. So when I call this, it's not really clear which one's the numerator, which one's the denominator. I mean, probably the first argument is the numerator, but I don't know. So what I can do is I can say new type, numerator, and I can change this type to numerator double, say. And so now callers are going to be explicitly forced to wrap the first argument in this numerator constructor. I'm not necessarily saying, you know, always do this or anything. This is just presenting an option. So yeah, using this technique, you sort of force callers to make an explicit decision about, okay, I want this parameter to mean this. And I think in general, when you're writing Haskell code, I think it's better to work with sort of more restricted types. So, you know, don't just pass around doubles everywhere when, you know, the double actually means something more specific, like meters or something like that. And a lot of times when you sort of make your types a little bit more precise, then you don't have signatures like this where it's like, you know, you're taking 3 doubles and it's unclear which ones means. You can be doing things like, oh, I take a length and a width, and, you know, I'm returning an area, or, you know, I'm taking a speed and an amount of time, and, you know, returning something. So, yeah.
Can you use this sort of thing to represent, physical dimensions for dimensional analysis, such as length, mass, time, energy?
Yeah, certainly. Yeah, I'm sure there's some Haskell
Bjorn
packages.
Buckwalter has a dimensional
Yeah.
package, and there's a couple of others.
Yeah.
It's a rite of passage for some people.
Yeah, and that is a very good idea. What's like all these catastrophes that are basically due to like treating a floating point as like having a different dimensionality that.
Like that space probe or whatever?
Yeah. So it's.
Say that again, I didn't hear that.
There was some like probe that like mixed up like metric or whatever and standard imperials.
Yeah.
Which is a fairly serious.
Yeah.
They thought that they were sending newtons, but they were sending foot pounds, vice versa.
Yeah.
Yeah. Okay, cool. That's all I got.
Thank you. Here. So, you chose a wonderful note to end on for me.